So for this lesson, we're going to be using a very famous story. It's actually one of Aesop's fables called The Crow and the Pitcher. You'll have a chance to watch a short video that kind of explains the fable if you're not familiar with it. We're going to use this story to do a couple things. We're going to be looking at how we can model with linear functions and how we can find domain and range within the context of a real world situation. So a linear function is something we've talked a little bit about in each unit that we've done so far. And linear, the word linear refers to the fact that these functions, when you graph them, they look like straight lines. And you may remember back to Algebra 1 that one of the, every straight line has an equation that represents that line. And maybe the most well-known version of each equation for a line is going to be the slope-intercept form, right? So this y equals mx plus b is our slope-intercept form of a linear equation, where the m in the y equals mx plus b stands for the slope of the line, and the b stands for the y-intercept of the line. And we've dealt a lot with linear equations so far. We've used them a couple different times, so this shouldn't be anything new for you. It says here, if you're given a table of values and you have verified that table represents a linear relationship, meaning there is a constant rate of change, meaning that every time you go over by the same amount, you go up by the same amount, you go over by that amount again, you go up by that same amount again. That's what a constant rate of change looks like. You can find both the slope and the y-intercept from that table and write the equation of the line. Find the slope of your line, you would use that rate of change, which sometimes is described as this formula, which is delta y over delta x. That delta symbol means change in. We sometimes use that rise over run version of finding slope, or there's another version where you take your 2 points and you say, I'm going to subtract the y coordinates, my numerator of the slope, and I'm going to subtract the x coordinates for the denominator of the slope. These are all really doing the same thing. But the idea is if you have your table of values, you can use two of those values, subtract the y values for the numerator, and subtract the x values for the denominator, and that would give you your slope. To find the y-intercept, or the initial value, we're going to look at our coordinate point xy, where the coordinate x is 0. So we're going to try and find, okay, where whatever x is representing in our scenario, whatever variable that x is representing, when it's 0, what is the y value? Because that is the y-intercept that will show up as b in the y equals mx plus b version of the equation. So let's look at a quick example where we're going to do kind of what's described up there. Suppose the gas tank in Brandy's car holds 20 gallons of gas and the car gets 32 miles per gallon. Her distance traveled on one tank of gas can be represented by the function d of x equals 32 times x, where x is the number of gallons of gas she used. This kind of makes sense, right? If we know her car can go 32 miles per gallon, that means for every gallon of gas the car is using, it gets to go 32 miles. That's pretty good gas mileage. We could find out how far she could go if we know how many gallons of gas she uses. If she uses 1 gallon of gas, we would take 32 times 1. 2 gallons of gas, we'd take 32 times 2. So this function where the distance based on gallons of gas would be represented by 32 times that gallon of gas. Distance based on gallons of gas equals 32x. So let's first of all name the independent variable and the dependent variable. So the dependent variable is the one that, remember, it depends on what this value is, what the independent value is. When the independent value changes, it causes a change in the dependent variable. So if we look at this relationship, oftentimes the dependent variable is going to be like your y or your d of x or f of x. The dependent variable is often going to be y or your function name like f of x. Oftentimes the d of x, f of x, whatever, it's kind of taking the place of y. So in this case, in this example, the dependent variable is going to be the distance traveled. distance traveled. Because the distance that she travels is dependent upon how many gallons of gas she uses. So what's our independent variable? Our independent variable is normally going to be the x variable in our situation or in our function. So in this case, the x is the number of gallons of gas she used. So this is gallons of gas used. Then it says identify the domain. So the domain, remember, is possible values for x. Now, if we're just talking about an equation that just says literally y equals 32x, right? If our equation just says y equals 32x, see if I can write 32x correctly, then the possible values for x could be anything we wanted. We could literally use any number we wanted for x, multiply it by 32, and that would give us y. We could include 0, we could include decimals, we can include negative numbers, we could use really big numbers, really small numbers. There's literally no number that we wouldn't be able to use in this function. But when our function describes like a real world situation, what we're really trying to ask about when it says identify the domain, sometimes you'll see it referred to as the feasible domain, meaning that feasible is a word that kind of means what makes sense, what is possible. So in this example, the feasible domain would be the number of gallons of gas she could use, but in a way that would make sense for what this situation is describing. So for instance, I said here in just some random equation that said y equals 32x, we could use any number we want for x, including decimals, positive numbers, negative numbers, 0, really big numbers, really small numbers. It doesn't all apply here. First of all, can we use negative gallons of gas? Well, no, we can't use negative gallons of gas, right? We're not going to drive our car and somehow gain gas. We also can't use more than 20 gallons of gas because it's specifically saying traveled on one tank of gas. So our feasible domain is going to be anything bigger, and then I guess it's 0 or bigger, right? But smaller than 20. So x is going to be anything that's bigger than or equal to 0. I suppose that her trip could be just her sitting in her car going nowhere in her driveway, meaning that she's using 0 gallons of gas. But it has to be less than or equal to 20 gallons because her tank only holds 20 gallons, and we're looking at traveling on one tank of gas. So the feasible domain, or the domain for our scenario, is 0 is less than or equal to x, which is less than or equal to 20. Just another way of saying x is going to be between 0 and 20. Now the feasible range would be the next thing we're going to look at. The feasible range. And so if we look at this scenario, if we can use the smallest number we can use for x is 0, then that would give us, let's see, well, d of 0 would be 32 times 0, which is going to be 0 miles. So our d of x is going to be at its smallest 0. And if we put 20 gallons into our function, we'll do 32 times 20, which is going to be 640 miles. So it's less than or equal to 640. So our range is anywhere between 0, again, that scenario where she just gets in her car, sits in her driveway, and doesn't drive anywhere, or 640 miles where she uses literally all 20 gallons of gas in her tank. Anywhere in there is the feasible range for our function. So we're going to be looking at, again, like I said, we're going to be looking at a fable called the Crow and the Pitcher, and we're going to be using this idea of linear modeling to investigate that fable and actually to kind of replicate it in a quick little experiment that we're